All right, so now what we're going to do is we're going to jump ahead to page 100 in the textbook. And so if you want to hit pause, do that now so you can get up to there. And conditions being what they are, we're going to have to expedite a few things and we're going to cut some corners. But we need to talk about waves. And here's why. We want to be able to talk about the fun stuff like special relativity, which tells us about time travel, and that means that we have to understand how light works. And if we're going to understand how light works, then we have to understand how waves work. And the best way to get a handle on how waves work is to first take a look at how sound does what it does. So, on page 100 is a rough sketch of a speaker that's going back and forth, making a sound. And as it does so, it compresses the air molecules, and then it pulls back, and the molecules are spread apart, and then it pushes again, and this pattern is moving in that direction. Now keep in mind that these particles are not moving like so. They're actually moving back and forth, but the pattern of compression is what's moving, the pattern. In fact, this is called compression. Which is no big surprise. In this pattern, where the atoms or the molecules are pulled apart, that's called rarefaction, a less common word. Now, if I want to describe a sound wave, it's going to be inconvenient for me to draw that picture each and every time. So instead, what we do is we use a sine wave. Now, the thing about a sine wave that you have to keep in mind is that it's not a literal representation. It's a convenient mathematical representation. In the same fashion that we've seen this little sketch to describe an atom, we all know what that is. Now, do atoms really look like that? No, they don't. But it's a convenient way for us to think about it. And similarly, this sine wave is a mathematical description that's convenient for us. So over here, I've got a little grid, which is about halfway down on your paper. I'm going to put a 100 hertz sound wave. That's 100 cycles per second. And I'll put this guy like so. All right, and we see that this wave has a certain length to it. We use Greek letter lambda, looks like an upside down Y. Lambda means wavelength, all right? And it will have a period of 1/100th of a second, which would make sense. Okay, 100 cycles per second, so each wave would have a period of only 1/100th of a second. Now I'll superimpose on that a 200 hertz wave. It's going to have twice as many waves as the 100 hertz wave, and so we'd get a pattern that would look like this. Whoops. Let me draw that again. This is why I hate dry erase boards. All right, so yeah, it would look more like this. Here we go. Okay. So you can see here the wavelength is much shorter. And that's exactly what's going on here. The relationship between frequency and wavelength is inverse. The higher the frequency, the shorter the wavelength. And the arithmetic of waves and frequency and the velocity of a wave is really quite straightforward. The velocity of a wave is equal to the frequency times the wavelength. It's that simple. All right? And that takes care of this first page, page 100. Now what we're going to do is we're going to skip ahead to page 101. On page 101, it talks about the medium, the role of the medium in a mechanical wave. And that's what we're talking about here. These waves, whether it's waves on the ocean or the waves in a slinky or sound waves, they're called mechanical waves. All right, so I'm going to clear the board. All right, the role of the medium in a mechanical wave. That's right. The medium determines the velocity of the wave. And so here at roughly sea level, in this nitrogen-oxygen soup that we walk around in, the speed of sound in the air is approximately 331 meters per second. And that comes out to somewhere around 740 miles per hour. And in different mediums, sound has different velocities. And some of you have experienced this without really knowing it. Imagine, well, summertime, we go swimming in the lake. You take a good breath of air, you go down a couple feet under the surface of the water, and then suddenly you hear, whee, and you think, oh boy, motorboat. And so what does everybody do? Well, they stick their head up, which never makes much sense, but that's what they do. They stick their head up to see where the motorboat is, and it's about a half a mile away, but it sounded like it was right on top of you. Well, for that's because the speed of sound in water is roughly 4 times the speed of sound in the air. So yeah, it's going to sound like it's a lot closer. So that's important to understand, that the medium determines the velocity of a wave. All right? Here's the other thing that we need to understand. We have to understand the Doppler effect. Okay, the Doppler effect. We've experienced this. We hear a car going by with a horn, and you're standing on the sidewalk and you hear, you hear that drop in pitch. Or down on the campus, we hear jets coming into the jet port, and it sounds like they're throttling down their engines. No, they're not. As they approach, that jet turbine is going to have a certain pitch, but as it goes overhead and is going away from you, that pitch is going to lower. So you can hear a lower pitch. All right, so what is it? It's the apparent It is the apparent change in frequency of a wave due to the motion of the wave source relative to the observer. All right? So it has to do with motion, and it also has to do with the observer. Okay? We need to know how this works. So let's imagine a car in a parking lot. So here's the car in the parking lot. And here's the observer right here. No wind. No wind. And that's important because what we're saying is that there is no motion of the medium relative to the observer. So, let's say this guy has a custom horn installed in his car, perfect concert pitch A, 440 hertz. The guy hits the horn, Those waves come out, 440 of those waves every second, moving across the parking lot at roughly 740 miles per hour. They get to the observer. Those waves hit the observer's ear bones. Eardrums go back and forth 440 times per second, and that's what the observer hears. Perfect concert pitch. Hey, now let's compare it to this scenario. Okay, now, again, no wind, but now we're going to put the car in motion. We'll say 35 miles per hour. The guy hits the horn. But wait a minute. Let's think about this. The guy hits the horn. And the first wave comes out. We'll say that's the first quick wave. And a split second later, the second one comes out. But what's happened in that split second? Well, the car has moved forward, hasn't it? And so now the second wave comes out, and what's happened is the distance between the first wave and the second wave has been shortened. And because they have been shortened, remember this relationship between frequency and wavelength. The velocity of a wave equals the frequency times the wavelength. And so if the wavelength gets shorter, the frequency is going to get higher. Ain't no way around it. That 35 miles per hour will not add to the 740 miles per hour. Those waves are still going to hit at 740 miles per hour. Why? Because the medium dictates the speed, nothing else. So those waves are locked in at 740 miles per hour, period end. So we get to a point where this is actually a something's got to give sort of scenario. So that's what happens. The distance between the two waves gets shortened, and therefore the frequency gets higher. That's how the Doppler effect works. And similarly, if the car was moving away, moving in this direction, the first wave would come out on its way to the observer. But by the time the second wave comes out, the car has moved down the road a little ways, and so the distance between the two waves has increased. And so you have a longer wavelength, and with a longer wavelength, you get a lower frequency. So that's the basic idea of the Doppler effect. Now on page 103, you'll see the Doppler effect formula as it's presented in most college textbooks. And this goes to my background, operating sonar in the United States Navy. And at the bottom you see a variant on that formula that is used to determine the velocity of a wave source. I'll just show this one briefly to give you an idea on how this works. Back in the days of the Cold War, we chased Soviet submarines. How did we do that? Well, we would drop these contraptions into the water called sonobuoys. They were long tubes, about that long, about that big around. We'd drop them from the air, they'd hit the water, and a little flotation collar would inflate, an antenna would pop up, and these microphones would drop down into the water. And it would listen. It would listen to the sounds in the water. So let's say that we were looking for a submarine that we knew was going to make a sound at 80 hertz. And why would that be relevant? Well, in the summertime, when you're sitting there in your living room, you have the living room windows open and you hear a Harley Davidson drive by, you don't have to get up and look out the window to know that it's a Harley Davidson. Or a vintage VW, they have a sound all their own. Well, similarly, a Russian-built submarine is going to have a different sound than a French submarine, or a British submarine, or a French submarine, or a United States submarine. They all have their own unique sounds, and we knew what those sounds were, and that's what we would look for. So, we would put a pattern of these buoys in the water, like so. And this is a symbol for a sonobuoy. And they might be, oh, say 3 nautical miles apart. And each one would have its own channel. Okay, 1, 2, 3, 4, 5. And then we sit and wait. And here's how it might very well play out. So after a while, we'd start picking up a signal, a sound in the water. And buoy 1 might pick up, say, 80.5 hertz. And buoy 2 would pick up 80.0 hertz. And buoy 3 would pick up 79.0 hertz. And buoy 4 would pick up 81.0 hertz. And buoy 5 would pick up 80 hertz. And you see that they're all different frequencies, slightly different frequencies. But from that, we could tell that that submarine was right here, using Doppler effect, heading directly toward buoy 4. All right, so buoy 4 is slightly higher than what that sound ought to be, heading directly away from buoy 3, and there it is, 1 hertz lower than it ought to be. It's right abeam of buoys 2 and 5, so it's right dead on 80 hertz. And it's kind of heading toward buoy 1, so the frequency is slightly raised. And that's just the basic physics of it. On the next page is an actual example. So on page 104, there's an example. There is a typo on this one. It says on the example that the speed of sound in water is 4,900 feet per second. That's supposed to be 4,500 feet per second. But in any event, here we have a sonar analyst detects an underwater sound at a frequency of 319.63 hertz. He knows from prior intelligence that the sound is actually propagated at 318 hertz. Determine 1, is the sound source approaching or receding? And 2, what is the speed of the sound source? So, what we'll do is use the Doppler effect formula. The velocity of the source is equal to the speed of sound times the changed frequency minus the original frequency divided by the changed frequency. All right. So now we just plug in the values. So we know that the speed of sound in the water is 4,500 feet per second. The changed frequency is 319.63, I think. Yes. Yes? Yeah. Minus the original frequency, 318.0, over 319.63. Okay, so now it's just a matter of crunching the numbers again. So that should be 4,500 times 1.63 over 319.63. I got 73.35. We'll divide that by 319.63. I got 22.948. Feet per second. Okay, now we're going to turn that into nautical miles per hour, or knots. So I'm going to round that to an even 23 feet per second. 23 feet per 1 second. Feet. I'm going to replace that with a nautical mile. Second. Replace that with an hour. Okay. 6,000 feet makes 1 nautical mile. 3.6 times 10 to the third seconds makes 1 hour. Cancel, 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 cancel. Equals 23 times 3.6 nautical miles over 6.0 hours. .8 over 6.0 . 13.8 nautical miles per hour, or 13.8 knots. And that's how it's done. Now, the reason I did that is because I wanted you to see how cut and dried this whole idea of how the Doppler effect works. And there's really not too much that's nuanced about this. This is pretty much meat and potatoes, basic physics. So yeah, do remember this. I'll probably throw you a Doppler effect problem for you to work out. But that's exactly how you do it. And compared to some of the other stuff we've been doing, this is pretty straightforward. Use a formula, plug in the numbers, let it rip. All right, so there we go. There's the Doppler effect.